hosting a few other jobs. And in this particular college, I'll be looking after research in nanotechnology projects and teaching the PG people, PG students, especially in chemistry, and at the same time addressing all the people to work towards nanotechnology, because it is an interdisciplinary or multidisciplinary subject where you have profound applications in each and every subject. So you cannot say you're just a nanotechnologist or work with something on the nanomaterial. It does have most of the applications in most of the fields. And this I'm trying to bring out for the audience, students especially, to understand what exactly it is. And I hope at the end of this particular lecture, some of the students might be inspired to take something relevant to their subject in nanotechnology. Yeah, at the outset, I started my career as an analytical chemist from Hyderabad JNT University, and then I moved on to different things, to chemical physics, and then environmental chemistry, optophotonics as a postdoctoral program in Lawrence Berkeley National Laboratory, where we need to develop and synthesize the materials for the waveguides and fiber optics, which they call it as a chemistry synthesis, and they've taken me into this particular program, though it is not really related, but mainly it is applied oriented. So we have to take up this, and it gave me some additional knowledge which is helpful for me in doing cross-disciplinary research. And then in applied technology, where we are working on nanomaterials, nanosensors, MUTAs, hybrids, MOCs, metal oxide composites, polymers, what else and what not. If you see an application related to these things, we apply that in that particular area or that particular field, so that it is useful for the society, industry, as well as for the academics. So that's why we specifically call as applied nanotechnologists, because our problems doesn't come from our side or from our group. It directly comes from the industries for us to solve and provide solutions. So we start from the material synthesis to packaging, device fabrication, integration with electronics, and then commercializing after publications and patenting. That's what we do in these particular areas. And now we started a new group in electrochemistry, a new group in nanotechnology, which is nanoelectrochemistry for biomedical science and biomedical molecule analysis. I have 2 or 3 slides on that particular subject. So in addition to these things, we also work in the field of pharmaceutical, medical, mechanical engineering, electronics and communications, and petroleum engineering, computational studies, which we recently added to our programs of research. And at the same time, we are also trying to switch between biomass gasification towards sustainability. This is in brief what our group does. And some of the key technologies that have been developed over a period of time, say 9 to 10 years, these are simple lists of things, and all these are evidential with the help of publications and patents. And some of might be of your interest to the students in application side, some might be for the interest of faculty members, especially in electronics and the chemical physics. I mean, I don't want to distinguish between the subjects, because once you go into the advanced research, you need to know everything. Maybe 50% of your subject, but rest from other subjects you need to integrate, make them useful for your purpose, and make them understand after you publish these things. So in that particular area, we were able to publish and have patents in so many other areas. And these are some of the key technologies away from analytical chemistry that what we have developed over a period of time. Yes, this is the list of publications. I mean, I'm going to skip this one. And most of the publications are evidential from research projects that we have done, helping our university, college where we work, and at the same time bringing in some revenue in terms of patents and in terms of book chapters, etc., etc. This is just for information. I'm going to skip this. Yes, coming to the entire topic, nano applications and applications for sensing and electronics. First, why do we need nanomaterial? Why do you need to minimize? Why do you need to go to the micro area from bulk material? So I start the first section with miniaturization. This miniature has been started probably in the early 1980s, but by the time we start our PhD in Germany, during that particular, these industries in US, they have released a roadmap stating that these miniaturized objects are purely useful in hospitals. Probably they started in early 1995, where they want to use these miniaturized devices for hospital, laboratory care, point of care diagnostics using cell phones, because during 1999 and 2001, these cell phones are really scarce, and only the rich used to have these cell phones because of their expensive nature, and so it is not usually available for most of the people. And subsequently, they went into a stage of by the year 2015 to implantable devices where they can use the sensing, monitoring, and integrating that with electronic circuits and packaging, and subsequently implanting them for various applications. So with this, Miniature has come up with some of the examples that I'm going to show. If you see in 1950s, you have an air conditioner of huge size, and this is just nothing to do with the lecture, but to give some visual experience for you how the size of an equipment in 1950s is going to be compared to the present day status. And if you see something in 2020, you'll be shocked to see this particular air conditioner is going to be a wearable one, almost the size of 5 centimeters. An air conditioner with 5 centimeter size, you can see the size reduction, feel the size reduction from over a period of few decades, how it has come down to this thing. This is the one in 2020 where you have a wearable device as an air conditioner, and we can call it as a personal air conditioner, which has recently put to market in July 2020 by Sony. And I'll give another example, which most of you know, how the cell phones have evolved over a period of time, from being 30 centimeters in size to almost like 4 to 5 centimeters inside, almost like a business card. And since your expertise is in electronics, you can easily understand how the size of transistor has come down from 10,000 nanometers to almost 6 to 4 nanometers, and it is still in the progress of going down, further reaching the size or close to atom size. And most of you know what is a flash drive, what is a USB drive, or what is a hard drive, and types of hard drives, SSD and HDD. And in 2002, where I purchased my first flash drive, which is 32 MB, and it costed nearly 10,000 rupees. And now in 2020, you have the same size, but the volume is going to be 2 terabit. This is where miniaturization or nanotechnology comes into picture, so that you can minimize, increase the capacity, and in 2024, it is going to be like 64 TB in your USB flash drive. And if you take SD cards, the same size in 2005 is hosting 128 MB, and in 2014 it went up to 1 TB, and in 2020 it is coming up to 1 TB with the same size, same space and size. And as of now, if you talk about HDD, it's already crossed 15 terabit in 2018, and as far as SSD is concerned, it crossed 100 TB in 2020 by Nimbus data. This is all some of the examples, astonishing examples, where nanotechnology can do amazing things in reducing the size and at the same time increasing the space or requirement of our parameter. But why do we go for miniaturization? Because it has several advantages. Though it might have one or two disadvantages, but it does have meaningful advantages like minimizing the energy of the entire device. And also, once you minimize the energy, the device is going to be smaller, and the materials consumption to manufacture this device is going to be simpler. And you can integrate these things into several platforms, and the statistics of the results output in terms of redundancy in errors of these particular arrays can be reduced and understood easily. Integration is possible and it is simple. At the same time, the power budget is going to be reduced. These can be faster because of simple technologies that have been used. They are less in weight, so easy to carry. And at the same time, if you talk about sensors, the precision is going to increase, accuracy is going to be great, and at the same time, increased selectivity and sensitivity and reproducibility. And often, there is a possibility to integrate into the new profile devices that are going to come over a period of time, and this can be accommodated in a portable way. So with all these things, in addition to that, they also have some negative impact. some of the things like some materials may not be biodegradable, but the minimal effect is can be ignored and it can be utilized in a better way. Material toxicity is also another thing, and job losses because of integration and automation and robotics that do come into the picture while preparing the miniature devices. All this can be understood, but more advantages than disadvantages made a way for this to get into commercialization. And if you see here, these are some of the microfluidic devices and pharmaceutical devices where it has been increased in number. The percentage shows people are liking and it is acceptable by the society in terms of miniaturized devices, specifically to the cost orientation. And we started to work on gas sensors after seeing these microfluidic lab on chip devices and MEMS based gas chromatography. Gas chromatography is a big one, almost it occupies the size of half the size of a room. But these people have converted entire thing into a small 5 centimeters unit where one is the gas chromatography, which can perform most of the gaseous operation, and there is a lab on chip where it exactly performs entire functions of a diagnostic center on this particular chip of the size of 10 centimeters. And moreover, these two smaller miniaturized devices and sensors are highly accurate in terms of design, architecture, assembly, integration, and packaging, where they found some of the problems in packaging, but they have overcome later on. But these two perform exactly in the same way as the macro devices. So, with this, since people have started gas chromatography, we thought of getting into FTIR spectroscopy because that is the area where I work on. So, we want to miniaturize that. And during that particular time, we have seen GC based microsensors, fluid gas sensor or volatile gas sensors, micro cantilevers, and infrared based gas sensor. With this infrared based gas sensor, we thought of developing our own system for gas sensing in parts per billion levels, not in parts per million, but in parts per billion and trillion levels. And the size of this particular system we designated as 5 to 6 centimeters, not beyond that. We started with broker FTIR. We replaced the sensor head and we have developed something for seawater analysis where the analysis component, which has obtained from this front end sensor head using the same electronics but a different layout and architecture, is exactly the same. And this has been published in Applied Spectroscopy. And we started with a miniature setup for FTIR where we use the interferometer for analysis, but actually we have removed that one by adopting to hollow wave technology and incorporating another Winston cone. This simple module has been converted into small 10 centimeters units for FTIR analysis with the same source as well as same detector, what we use in commercially available sensors. So we went for a review of available handheld miniaturized devices, but most of them are highly expensive. So we want to have a low and very less expensive FTIR for gas sensing in parts per trillion levels. These equipment gives only in percentages or parts per million, but we are targeting parts per billion and parts per trillion levels. Initially, we failed in getting parts per trillion, but somehow we ended up in 100 ppb levels, so that is close to parts per trillion. So we are happy with that. And at that particular time, people have developed from University of California, Davis Center, Scott D. Collins professor, have developed just a 5 to 6 centimeters or even less than that one on a wafer, which is nothing but an interferometer, which has been compared with the commercially available large FTIR. The interferogram signal looks exactly the same. So this has been put to practice for applications in gas and liquid sensors. But the only problem with this is vibrations and other related. It has to be closed in closed atmosphere, and it should be protected from vibrations and acoustics. That's the only thing. The rest, it exactly performs like a commercial FTIR. And then we entered into another program where we want to have a small 1.5 centimeter FTIR, which we call it as a microspectrophotometer. This has been developed. I'm partially involved with this particular program where they want to lift this particular FTIR into space. Preparation of this particular FTIR has been done, but sending this into space has been stopped because of political reasons. It was still lying in Science Council of Taiwan, but not at launch. It was supposed to be launched into space by MSAT program. This is a typical satellite program, which is hosting our NUTAS and FTIR systems. And some of the examples, if you take the miniature devices, you can see the smallest capsule for endoscope. You can see Jet Propulsion Center laboratory sensor, which is almost the size of a dime. And you can also see the smart IT sensor, which is on the palm. So these are the simple miniature devices which we have inspired for taking and talking to these people. And we have noted some of the sensors, like medical telesensor chip, which is on the tip of your finger, where it can measure the temperature and at the same time it can transmit the body temperature to other devices. And you have a IR microspectrophotometer for blood analysis, gasoline octane analysis, and environmental monitoring, which is again 2 centimeters in size. This can also be used in chemical warfare agent monitoring, and this can also transmit. So similarly, the entire optical bench of 1 meter came down to 1 millimeter size. These are the advantages of miniature sensors. As I show you the endoscope capsule, and we also have a RFID sensor, hologram, and microscope almost double the size of a dime. So inspiring from this, and also people like other departments and our colleagues working in the field of nanotechnology, we ventured into this as a postdoctoral program, where we were fascinated by the integrated application of this nanotechnology, where it combines the biological principles of the materials and the laws of physics and chemical properties of these materials together into one, so that you can clearly develop something in a different way. So our publication volume has increased because we published with the macro sensors, then converted to micro, and then converted to nano sensors. And after converting it to nano, we went into nano arrays. And from nano arrays, we went into wireless sensors. So typically one exact work combining with different platforms, we resulted in 4 to 5 papers. So since this nanotechnology is going to be key enabling technology with the volumes of sales reaching billions, and it also has significantly benefits to environment, and it can be applied in each and every subject. So we ventured into it. Since then, we used to get most of the industrial problems for us to solve. So with this, we were able to do everything related to industrial applications, and that's how we entered into applied nanotechnology. I'm going to skip this one because it is most of you are aware. And why do we use nanomaterials for sensing? Because it has simply improved physical and chemical properties. And if you use some of the dopants and if you change the architecture or layouts of this, that itself can act as a sensor. For example, if you take a single wall nanotube or multi-wall nanotube, just entwining them can change the resistance or conductivity within the tube. That itself triggers the difference between before and after contact with the gas, and so on. It can act as a sensor. So, and additionally, these nanoparticles have unique properties. Like, for example, opaque substances become transparent, like copper. Inert materials become catalyst, platinum. Stable materials turn combustible, aluminum. And solids turn into liquids at room temperature, gold. Insulators become conductors, silicon. So with these properties, we use these metal oxides and metals as dopants, and we prepare different things. As we see, the beauty of these nanoparticles or nanomaterials or nanostructures, you can prepare them wisely if you understand what exactly you need and what exactly you need to show. For example, you take different fields, starting from immunology to electronics and magnetics and optics, and you take a property, any property, that has been enhanced only because of scale length modification. That means it is going to be in nanometers, and once you have nanometers, you have an enhanced property in different subject, and this scale dimension is going to be in nanometers. And another beauty of this particular thing is you can synthesize very easily. You have n number of parameters in synthesis of these nanomaterials. Suppose if you change the temperature as one of the parameters that has to be that has to show variation, you can get different types of nanostructures. See, you have almost 12 varieties of zinc oxide nanomaterials just by varying the temperature. In the same zinc oxide, by varying pH, you have 4 different types of nanostructures synthesized. So this is one of the beauty. By changing the parameter, you are going to get these things. And as we already discussed about nanotechnology and nanoparameters, nano is giving a very big opportunity in different sectors like semiconductors, medical, aerospace, textiles, environmental, and etc. etc. This particular thing is going to boost the inspiration of a young researcher to get into nanotechnology. And since we talk about different sensors, why do we need these sensors particularly? There are so many other driving factors for these particular sensors, and these are like social sensors, legislative sensors, technological, political, and economic. For example, if you take legislative, health and safety, environment, avoiding prosecution, these are the legal driving factors for developing sensors. It can be monitored everywhere. And if you talk about economic, you have testing materials, cost, process, automation, energy consumption, and trans-country control of the boundary pollution is for political factors, and technological factors like improved performance, sensing new variables, and at the same time precision and accuracy of the measurement. All these factors are the driving forces for these particular sensors, especially nano and micro sensors. For example, if you go onto the street, you have different types of sensors. One, to conserve energy, means you don't need a traffic light on the during the daytime, so it has to switch on and switch off by itself. So it has been pre-programmed, so you can conserve energy. You need to have high lux units. You need to have public safety. So you need to have a brighter light, and it can be simpler, faster to deploy. Maintenance costs are reduced, so it is being pre-programmed. So all these things, additional advantages that we get from these particular sensors. For example, if you talk about something on smart office or smart home, unknowingly we have so many sensors within the office or house, like motion sensor, automatic switch on of lights, door control, window control, environmental monitoring for the gases, temperature, heat, and moisture, lighting control, remote infrared control for your electronic device, etc., etc. But if you take an automobile, typically minimum of 135 sensors are available within automobile. And if you take anything like a smartphone or even a chemical reaction where it can be controlled by a sensor, you can use minimum of 4 to 5 sensors to have a proper monitoring technique. And these are some of the examples where we have sensors in an automobile. So if you take any type of device, it ends up with a minimum of 10 to 15 sensors. For example, if a typical sensor, since we are talking about gas and liquid sensors, it needs to have a precision, accurate, and it should be stable. It should give proper results, and it should be very reliable. At the same time, it should be less expensive, low power budget consumption, and it has to be compact, and it can be integrated so that it can be utilized on a larger scale with so many integrated applications. And now it is going to add a smart sensor where it can be combined further with to have a decision making system for this particular sensor utilizing data science and robotics or IoT or artificial intelligence. This is a typical polymer sensor. Once you have the swelling in the polymer, the chain breaks up and you have a limited signal, and that is converted into our chemical signal. And typical chemical sensor dynamics looks like this. You need to have this thing. You need to have all these characters for a typical sensor. And another important thing that you need to have in a typical sensor is going to be 3S and 3R. One is sensitivity, selectivity, stability, which is what most important. Otherwise, we don't know where the signal is coming up. And it has to be reliable, repeatable, and reproducible. Whoever it does, it should be reproducible, and the signal has to be very reliable to get optimum sensor gas dynamics. So, keeping this in mind, we have developed so many things, and one of the main reasons for us, our group, to enter into gas sensors using nanomaterials is the increased interest in gas sensors. This is evident through publications over a period of time. It has been increased by almost 10 to 20 folds. And this data is available up to 2019 from Web of Science. And so many materials have been developed. And we have chosen dopants and metal oxides as one of the materials for initial identification as gas sensing materials. And in addition to availability of all these things, we typically work on 2D materials and graphene, metal oxides, and carbon-based materials, and some of these hybrids taken either from ferrites or phosphates. So with this, we were able to publish so many things on so many gas sensor as a platform. Then another problem that we have achieved or we have seen is how do we get these sensor chips? What is the layout? What is the architecture that we need to have? So instead of going for the commercial things, we typically purchase a platform which is just a substrate which is made of alumina, and on that we started to screen print our interdigitated electrodes. At the end, it is connected to a platinum electrode. So different types of electrodes have been screen printed, different shapes, different variants, different arrays, and finally we were able to end up in a typical sensor of our requirement. And during those early days, most of the gas sensor respond at high temperature. That means you need to have a second circuit beneath the alumina substrate, which is for heating. A single millivolt change in change in electricity is going to give change in 100-degree temperature or so. So typically the platforms what we have used is covered with ruthenium oxide so that we get the required temperatures. But that is not the requirement of the day. The day demands, the society demands something as a sensor which is precise and works at a room temperature, not at high temperature. So ultimately we have to eliminate the heating element from the bottom, and then we have to develop something only with the sensing device. Our typical sensor looks like interdigitated two gold electrodes connected to a platinum electrode, and we have a sensing film. The entire thing is in the dimensions of 10 millimeters by 5 millimeters. This is the real picture of our sensor, and this can be put as an array, and at the same time you can use it as a single chip sensor for initial applications. So what exactly we do is we develop the chip and then coat it with our transducing material, then subsequent calibration and sensing study. And as I said, most of the materials we use carbon-based materials like graphene oxide, graphene fluorines, CNTs, and other metal oxides, dual metal oxides, doped with CNTs, triple metal oxides, inorganic, organic hybrids, polymers, composites, etc. All these things will be studied because most of the time we may get one or two as the best results, but at the same time, these redundant results will be useful for our experience to use it for different types of gas sensors. For example, when we are trying to use NO gas sensing, we got a good result that might be useful for NO2 gas sensing. So ultimately, we were able to develop NO gas sensor as well as NO2 gas sensor. We have used initially tin oxide, titanium oxide, iron-based tungsten oxide, indium oxide, and ferrites. So we use all these things initially, and in combination, we are using so many other things for specifically conductive polymer-based gas sensing. And we initially started with working on CO sensor using cobalt oxides, but the sensor is very good enough and it has a heating element. But the problem with this is it is responding at 230 degrees centigrade, which is very, very high temperature. And we were able to detect something in the order of 1000 ppm to 500 ppm. But still, the sensor is not in the market just because of one disadvantage, which is nothing but 230-degree sensing thing. So finally, we ended up developing a material, cobalt oxyhydroxide, adding additional oxygen atom into cobalt hydroxide, so that this particular sensor is going to be working at room temperature. Finally, we were able to do the sensing studies, and present day cobalt oxyhydroxide sensor works at 100 ppb levels at room temperature, and it is completely versatile without any interactions or interferences from other gases, as we have shown it here. And the sensor dynamics are going to be purely following the path as a textbook manner, and this has been commercialized as a small devices, which is a size in the order of 10 centimeters in countries, developed countries. And after that, we got another problem from the industry to develop ozone sensors using SNO2 material. This SNO2 thin oxide is not going to be giving a proper sensitivity result. So we had to add this SNO2 to other materials in different proportion. Finally, we were able to develop a TiO2 using hydrothermal methods. And these TiO2 and SNO2 in the ratio of 1:8, we were able to develop a ozone sensor where it works for detection of this particular ozone in the order of almost 250 to 200 ppm. And this also have been packaged and developed as a device, and this is also in industrially available, and it can be purchased by any person. In addition to these ozone sensors, CO sensors, and NO sensors, or the hospital medical councils have taken all these sensors, and they want to have ozone sensor, oxygen sensor, CO sensor, CO2 sensor, NO2 sensor, and hydrogen sensors in hospitals as a norm that they have prepared, and this work has been given to us to do these things. And another one, which is Indo-Taiwan project, where we have developed a NO sensor, where we initially failed, but the odd results gave us a proper setup. And in this, we were able to do something with 1:4 indium oxide, tungsten oxide, using the same sensor chip. We have a perfect dynamics. We went up to almost parts per trillion levels. 100 ppb is the one initial thing that we have developed, but we ventured into parts per trillion levels. And you can also see T90 and response T90, and these are perfectly all right for the project work. And later on, from biology department, where we were asked to develop something for formaldehyde sensor, where they use excessive formaldehyde for cleaning and so many other things within the biological departments, tissue culture, animal tissue culture, plant tissue culture, etc., etc. We started developing graphene-based sensor, but we were unable to convert graphene oxide into graphene because lack of inert atmosphere table or chamber. So we started to work on graphene oxide, but that itself proved to be very much useful, and we were able to develop something with graphene oxide for detecting 50 ppm. What they need is, the biotechnology industries, they need something in the order of percentages to very high ppm, but this one is coming up to 50 ppm. And after this has been extended by graphene-based sensor for formaldehyde detection, and that gave almost 150 ppb result using graphene compared to graphene oxide. And after that, since I said I'm going to take one of the examples from each category, we have hybrids for NO gas for enhanced sensitivity, what I have shown from indium oxide and tungsten oxide, which is the only beauty of this is these hybrids are being prepared microwave methods. And in hydrothermal methods, probably we need 3 days time to prepare these nanomaterials. And these nano hybrids in microwave method typically took 5 to 6 seconds. That means we have saved almost 48 hours in preparing these materials. And it also gave very enhanced results for NO gas sensing. And we also have something on this particular gas dynamics. And at the same time, faster response and improved characteristics for these materials, because these are hybrids. And the same thing we have used for ethanol sensing for meteorological department, where you used a different material as a heterojunction zinc oxide, copper oxide material as a solid state room temperature for measuring ethanol. This also gave very good result in terms of sensor dynamics, where you can see 150 to 250 ppm, and with a very good linearity. And this solved the purpose of developing a metrological standard for ethanol sensor. And using the same hybrids, we measured humidity, and later on, since our gas sensors, specifically CO, CO2, NO, oxygen sensors have been, ozone sensors have been placed in hospitals, World Health Organization has given us some additional work where we have to develop something for anesthetic agents, because the reason they have asked is the patient in the OR is being treated with anesthetic agents. Once the operation is done, he is out of operation theater, but the amount of anesthesia given to the person is higher than the concentration that is required for the person to be operated. So the rest of the anesthesia is freely available in the operation theater, and it is affecting the doctors and the support personnel who are regularly moving into the OR theaters. For this particular purpose, Occupational Hygiene Department of WHO has asked us to develop some sensor for anesthetic gases. Initially, very crudely, we have used a conductive meter for measuring these particular sensors, and this has been published in a 3.5 impact sensors and actuators journal, but very crude. And it took nearly 3 to 4 months for us to develop this particular sensor because we have so many stability issues. And we have studied this particular thing using the Molecular Studio software, and then you can see this redundancy in this particular thing, but still it is one of the best method and simple method to analyze anesthesia in various places. Because in earlier days they used to measure with integrated hyphenated techniques, means the cost of analysis is going to be very high. Each integrated hyphenated technique like NMR, FTIR, GC, and all these things are going to cost you something in the order of 1 crore. But with this particular sensor, we were able to measure something with less than 3,500 rupees. So this has been studied with a very high-end FTIR spectrophotometer, which is of zero point 0.01 wavelength resolution, and commercially available and hyphenated technique spectrum. And our results are completely the similar one. Only thing is cost has come down, analysis has come down time period. So we were able to propose this. So with different types of sensors available on each and every floor of hospitals, they have come up with a new problem. I mean, they are just to provide a solution. We'll have sensors in every floor, but they ought to be monitored from a ground floor or something in the basement. So typically they need a wireless sensor. So we have to modify all the sensors, whatever we have developed, into a wireless sensors. We took the help of Zigbee technologies from Hong Kong, where they supplied with the components, and all our sensors are segregated into two sections: sensing device and transmitting device, or receiving unit. And this particular part is going to be a sensing device, and the other one is a wireless receiving unit or a node to connect it to a host PC. So most of the sensors, whatever we have developed, initially we tried with 25 meters, and after that we were able to transform this to a distance of almost 500 meters. So most of our sensors have been transferred into wireless sensors. With typically gas sensor dynamics are going to be very reliable, and we were able to measure something in the order of ppb, and most of these things were also placed in hospitals for commercial purpose. And after that, in this particular year, based on our past experience in medical analysis, we were given epinephrine analysis, a neurotransmitter which is responsible for so many side effects. For this, our previous strategies did not work, but we have to come up with a new nano-electrochemical electro-oxidation mechanism so that we will be able to detect something in the order of lower micromolar concentrations, which we have done in January, and it has been published in the Journal of Nanoscience and Technology in this particular year, where they use HPLC-MS fluid fluorescence this with cobalt oxide and bismuth phosphates as a material for epinephrine, and we were able to do something in the order of 1.72 micromolar, the lowest where we were able to detect. Since we have different types of other systems where we can measure this electrochemical oxidation mechanisms of epinephrine, we started to do this with another PT doped SNO2 material with the same. Only difference is this material is a partial nanocomposite material. With this, we try to do something in a better sensitivity manner, and we were able to achieve something in the order of 0.35, much better, almost 4 to 5 times less than previous one that we have published in Journal of Nanoscience and Nanotechnology. And this work of partial nanocomposite from PT SNO2 material has been published in Journal of Chinese Chemical Society, that is also in March 2020. And in addition, we were also given with the better results, we were also asked to measure levosimendan, TMAH, and other types. And for sensitivity issues, we want to do so many other things like cutting off CNTs, what we do. With this, we were able to achieve something in the order of 5 to 10% increase in the sensor field. And with all these results, our group has been identified one of the top 5 groups by GE in anesthetic sensors. And we were given all these types of chemicals, and almost 50% of the work has been completed, but still 50% is still ongoing with different students of the group. So we were able to do something with this in order to have a typical sensor. Earlier, we collaborated with ethylene sensor development with Canadian government, and that ended up in developing a different types of gas sensors, especially in the order of PPP. But that turned out to be a very good sensor in healthcare system. And this project extended to $23 million project with Canada and Taiwan government, where we were able to measure ethylene in the previous sensor. With the same strategy has been adopted to measure acetone in breath. That means indirectly we are estimating the diabetes mellitus type 2 ailment bodies using this TiO2 nanowire sensors. And single TiO2 nanowire sensor does not give any proper result. So we adopted a strategy to have an array of sensors put together, and then we have done some mixed signal circuit designs in Canada, and finally gas test measurements, and finally we developed a typical commercially available handheld sensor which is specifically designed for ethylene, but this works for healthcare and medical purposes for identifying and monitoring diabetes by measuring acetone in the breath. So this is one highly commercialized thing in healthcare system. And later on, since we worked on nano materials of graphene 2D and 3D, people started to talk about wearable electronics. Means our first project also, which we applied for DST, has come up with a dual gas sensor using a single chip, and they don't want any concentrations measurement, but they want only acoustic signal to be coming out. So that means these people, they are going to use these particular sensors as a wearable devices, almost the size of 1 centimeter, to be put up on their collars. Means whenever there is a hazardous gas in beyond the concentration, this particular sensor give an acoustic signal which is very close to your ear, so that the person, the soldier, he can identify the toxic gases that are being present, not to go in that particular direction. So this is the typical dual sensor for wearable type to be used in military soldiers and the defense application. That also we developed, and with that we entered into sensors and materials for electronics. And we were also inspired by a simple biomass chip, especially for drug delivery, which is being developed in Switzerland by Tech insulin pump, where it pumps in insulin by being present in the watch or beneath the watch through a nano needle. It injects and it controls and monitors everything without the knowledge of the patient. Like that, we were also inspired by so many other accelerometers that are being available. So we typically want to develop something wearables using electronic materials for health purpose or soldiers or any other thing. So like that, we were able to talk about and do something in the wearable electronics. Like different types of wearable electronics are available. We have developed something for smart shoes, where we have a barium titanate material as a nanomaterial. We use it right above the sole. What it exactly does, it because of the pressure that we incorporate on the shoe, it harvests the energy that is being generated, which is nothing but piezoelectricity. And this has been used for some other purposes whenever we require during the course of our purpose. And similar to that, we have so many things like smart glasses, smart watches, and we are working on something for sweat monitoring and at the same time generation of energy using these particular things, like using a graphite as one of the materials where the circuits cannot be printed. You can take a typical graphite pencil and you can design your own circuits on the skin. And this can either use it as a sweat sensor or use it as a energy harvester. And if the energy that is required for this is not sufficient, you can increase the area of this circuit by simply connecting two different circuits into one using a graphite medical wearable pencil. So this is typically no need to buy, just have a graphite pencil. You can design using your own. This also recently that has been developed and came into existence in July 2020. This we are also working on different types of for materials for implantable electronics and flexible electronics and wearable electronics for health and fitness and for the comfort of the patients, comfort of the person who is going to use this particular sensor as a smart sensor, etc., etc. But not all these things are being covered by our group. We are specifically working on cost-effective wireless and smart sensors. Means earlier micro sensors, macro sensors converted to micro, micro to nano, nano now wireless, and this wireless we are adding an additional parameter like smartness, so it becomes a smart wireless sensor with novel integrated in situ technology, chemical technology, and combining all these things, we are going to have a multiple output so that it can be utilized for different varieties. Like recent thing is skin-inspired wearable electronics for humidity, mechanical sensing, and temperature sensing. These are very, very simple, and the same thing can be transmitted or transferred to biological purposes for sensing different types of viruses, bacteria, and identifying the toxicity levels using these particular nanosensors. Just by simple alteration, you can develop these for those applications as well. And instead of going to a hospital and standing in queues, you can be monitored by having wearable electronics on your body, and these can be transmitted to your personal doctor, and at the same time, remedy can be obtained. And if the sensor is going to be smart enough, you people are going to be directed, or decision has been taken by the sensor itself, and you will be made convenient, timely, portable, and also completely comfortable without any problems by these wearable health monitors. People are working on these smart devices right now. And in addition to that, people are also working on implantable devices for bioelectronics, drug delivery systems, and at the same time, something from a wearable energy harvesting device where they supply this energy to these devices, and so many other things. All these things are going to come up. And we were also asked to develop something on micro air vehicle technology for identifying or sniffing explosive materials in various crowded places. So the sensor is going to be a very simple one, and at the same time, the sensitivity is going to be very high. So there is a chance of monitoring different areas with these small sensors. But they want something in the form of micro air vehicle technology, which can float in the air and at the same time go to different places. That is one which we are lacking. But people are working on these particular devices to identify explosive materials as a sniff sensors from very, very small wearable devices so that it can be achieved probably very, very soon. No, typically they are asking us our sensors to be very smart. And as I said, like miniature devices, it has a lot of merits, and at the same time, it also has huge number of applications in varied areas, in physical type sensors, chemical sensors, biosensors, or biomedical or mechanical, whatever it is. And it also has some of the demerits, like initial huge and investments in preparing these, and also complex procedures that you need to invent to get into simpler procedures, and prior knowledge is required to integrate these things, especially when you talk about the safety of these materials and devices. And some of the publications that we have in electronic materials, for example, copper metamaterials, which we prepared by taking some of the Vedic leaflets. From these, we prepared this metamaterial. This has been applied as a web browser, and it has been published in Electromagnetic very recently. And we also have a wideband microwave absorber antenna array, which is also published in Electronic Materials last year. And we have some of these graphene materials, doped metal oxides, as an array for DRDO projects, which has been published in Elsevier publications in Optic, and Theoretical Nanoscience, which is an American journal. And recently we have synthesized these materials in a green methodologies, and this has been published in Elsevier book chapters. We have two in this particular year: Handbook of Green Nano Synthesis of Nanomaterials and Compounds. So, like that, we are also working on different types of electronic sensors towards increasing the output per hectare or yield per hectare as per the guidelines of ICAR, where they need MEMS-based sensors which can utilize green chemistry practices so that the yield can be increased. Suppose if you see this particular illustration, you can see small countries like Indonesia, Bangladesh, Sri Lanka, Brazil, Thailand, they have higher yield per hectare compared to India, which is at 2.9. And this, they want to bring it between 6 and 7 by ICAR. So they want to venture into this by having sensors, MEMS, and also green practices. So with this, we one of the group of team of ours is been working on these particular sensors so that the yield can be increased. And one group is also working on drip irrigation system, where in the drip irrigation system, the sensor monitors how much percentage of the drop is really going into the plant and how much is the wastage. So these are smartly directed drip irrigation systems for the plant to take up entire thing, and also take up fertilizers, other minerals required for the growth of the plant. You need to have higher crop productivity. So two teams are working on this MEM sensors. One is on productivity increase, the other one is green practices, and the third one is smart usage of water by the plant. And as I said, this is going to lead to precision agriculture. And these MEM sensors can be used for soil monitoring, environment monitoring, velocity measurements, and photosynthetically active radiation, which helps in more productivity. So all these things can be worked out. And also, we are also working on different materials that they may cause stress to the plant. It might be biotic stress or abiotic stress. Typically, our sensors are based on limiting abiotic stress, but still, it can also be used for measuring biotic stress so that high agriculture produce can be achieved, and precisely use costly agrochemicals or limited the use. But at the same time, advancement of nanotechnology and green chemistry procedures will reduce the loss and increase the agriculture production. So with this, there are so many other varieties where people are trying to use in different types of RAMs in electronic industry using nanotechnology, MRAM, SDRAM, static, dynamic, so many other things, and people are using magnetic RAM, etc., etc. That I'm not going to cover here because it is already taking a lot of time, and we need to give some time for the audience to ask a few questions. So typically, these are the nanomaterials for nanoscale sensing at the levels. You can use different strategies, different layouts, different architecture to develop and refine your sensor till it goes to commercial level and publish so many things. At the same time, you can use catalytic, magnetic, or optical strategies for sensing schemes. And you can also eliminate by complicating your layouts. You can integrate these things in different things so that you can go up to zeptomole detection. Zepto in the sense you can go to concentrations which is 10 to the power of minus 21 in the biomedical scale, and you can integrate them for removing toxins, and you can also use them as bots so that many things can be performed in gas and gas or liquid in gas measurements, and so many other things. But one important thing before we apply for so many fields, the safety of this particular material has not to be avoided. So one has to be very careful in utilizing and working with these nanomaterials, and the direction given by nanotechnology committees should be properly understood, read, and the standards and legal procedures in nanometrology and nanostandards should be utilized for a cleaner, better, and greener environment, so that we always strive to enhance our comforts. This particular field can also aid in producing more yields, giving greater comfort, etc., etc. And these are some of the areas, selective areas with the different types of material that we utilize and work in our departments towards sensing and electronic applications. And with this, I'll give some of the references which might be useful for you people, students or the faculty, in terms of working related to safety of these nanomaterials and other regulatory issues that are being involved in synthesizing, working, and developing these things. And with this, I'll acknowledge my team, my students, my collaborators, without which this is not very much possible. And at the same time, more research is going to come up in this year and next year. So I'll try to close this and keep this lecture open for questions if you have. Thanks for your attention, and thank you for having me for this webinar. Thank you all. And if you have any questions, please.
Any questions? Thank you, Dr. Murthy. It was a very elaborate and informative lecture. You have given insight of many very advanced and complicated technologies related to the nano. Any questions?
Yes, I have a couple of questions.
Yes, please.
Okay, once it comes to the gas sensing, if we focus only on one gas, but for example, if we in environmental monitoring, if we focus only on carbon dioxide CO2 sensing,
Yes.
but the problem is there are other gases as well. So how we have to make sure the selectivity in this case? And the other thing is, so the resistance is also changes with the temperature and any other parameters. So how can we compensate the sensor with those cross sensitivity and selectivity?
Yes.
That's my first question.
Okay.
And the second question is how the nanotechnology or MEM sensors compete with the fiber optic sensors, because fiber optic sensors is growing very, very rapidly recently since 10 years. So how can you compare these two different kind of technologies for sensing?
Okay. Coming to the first question, CO2 sensing selectivity.
Yep.
Every gas responds to every material.
Sorry, the host went quiet. Sorry.
Sir, we are not able to hear you. We are able to hear you, sir.
Please unmute.
I request all the participants mute their mics so that Dr. Murthy can answer.
Can you hear?
I request.
Now we can hear. Yeah.
Okay.
Or we couldn't.
Okay. If you can hear me,
Yes, sir.
yeah.
Yeah.
You have to identify the material and you have to identify the interferences with those particular materials. Once you combine and try to understand the strategy, one of the respondent material, which is of not your interest, can be used as a dopant in the specific material of your interest. With these trial and error methods, you can increase your selectivity and sensitivity. And at the same time, you can also dope these particular materials with either carbon materials or other metal oxides like the gel metal oxides to rectify the signal that is emanating from temperature or moisture, so that with all these three different types of integrations and dopants and mixing, you can end up in developing a material which is highly sensitive, selective, and at the same time interference free. So these trial and error mechanisms only will fetch you a proper result. Okay. And in terms of second question, what you have asked about fiber optics and MEM sensors. I am also from fiber optics material, where we have done different chalconized based fiber optic as gas sensors. But if you talk really about sensitivity signals, they are rapidly developing, but the signal is not that good as these MEM sensors, where resistivity plays a very important role. So we skipped from fiber optics to waveguides. From waveguides, we entered into metal oxides based MEM sensors.
Yeah, but they have their own advantages, because if you use fiber optics, there are their advantages because
Yes,
they can survive harsh environmental capability
that's
and the
right.
selectivity and the immune to electromagnetic interference.
Yes.
If the application requires high temperature
Mhm.
environment, so
Mhm.
in that case, fiber optics is the best option. So
Fiber optics is the best option, but if you really talk about complex arrays and complex places of establishment, it involves a lot of costs, and at the same time, it involves a lot of investment into those things. So they are obsolete. And fiber optics sensors for aryl chemicals is going to be very obsolete instead of gas sensors. So it also has its own disadvantages compared to MEM sensors. Okay, next question if you have any.
Any other question? Yes. Yes. Arshad? Do you have any question, Arshad, please?
Please go ahead.
I want the PPT.
Can you repeat the question, please?
करो बेटा करो सोचो ना बेटा कुछ
Also, if the PPT is possible.
question?
I have one final question. So
Yeah.
you said we can combine sensors and actuators together. So is there any literature is on those combining sensors and actuators, and also is there anything combined sensors with the artificial intelligence for the smart sensing?
Oh, there are plenty of things available because if you consider sensors and actuators, if you go into automobile industry or automobile related sensors, you can find plenty of types of sensors.
नहीं पता हम सिद्धि वही वही कर रहा है अभी तो लड्डू
And these sensors are available with robotics